As has been well documented globally, we have observed and experienced the impacts of polar ice coverage rapidly decreasing year on year. The existence of positive feedbacks that create a feedback loop is hugely influential in regards to polar environments, in this case Arctic ice coverage. As will be explored in further detail later, we can see the loss of Arctic ice coverage impact various other aspects of our environment, which in turn only increases the rate of ice coverage decline. As can be seen in the figure shown on screen by CMISO 2003, this is the colour-coded daily ice concentration map for the Arctic ice extent minima for each year from 1979 to 2000, with each map representing the perennial ice coverage at the end of each ice season. We can see a clear visual decline. This rapid decline of Arctic ice coverage goes hand in hand with the loss of permafrost regions in high latitude areas. Initial studies, such as those conducted by Tunakai et al. 2009 and Zimov et al. 2006, have examined the extensive quantities of organic carbon trapped within these northern permafrost zones, which they believe to be about 1,700 billion tonnes, with the risk of this entering the atmosphere an ever increasing reality. With ice coverage declining and permafrost regions becoming increasingly exposed, the vast quantity of greenhouse gases that remain stored locked within the permafrost are becoming increasingly vulnerable. As highlighted by Collins et al. 2013, high latitude temperatures have increased twice as fast as global average, rising 0.6 degrees per decade over the last 30 years. Consequently, thawing rates are accelerating, therefore allowing for trapped organic carbons to break down into CO2 and CH4 by soil microbes to escape the cryosphere and enter the atmosphere as greenhouse gases. This warming only fuels the accelerating issue of declining Arctic ice coverage, as emphasised by Brown and Romanowski 2008, Romanowski et al. 2010 and Scher et al. 2008. The importance of Arctic sea ice coverage in the global climate system is largely derived from its central role in driving Northern Hemisphere ice albedo feedback, as reported by Holland and Bitz 2003. Zhang and Walsh 2006 and Holland and Bitz 2003 both report how this feedback results from the large contrast between the albedos of sea ice and open water. General circulation models consistently show there is a reduction in sea ice area driven by changes in external forcing. External forcing, such as increased greenhouse gas concentrations, is substantially enhanced through the resulting increase in solar heat input into open water. As can be seen in the next figure, again produced by CMISO 2003, it shows the average ice minima from 1979 to 1989, 1990 to 2000, and the difference between these two, as well as a prediction for 2050. We can see a clear decline in ice coverage and begin to understand the change in Arctic albedo.
Yamamoto Kawai et al. 2009 highlight potential issues caused by an increase of greenhouse gases on marine life in the Arctic, as the increased uptake of CO2 by seawater causes the concentration of hydrogen ions to increase. This increase of hydrogen ions changes the chemical equilibrium of the inorganic carbon system, thus reducing the concentration of carbonate ions, which are required by marine calcifying organisms, such as plankton, to produce calcium carbonate. With this ability to produce calcium carbonate diminished, key links in the Arctic ecosystem become vulnerable. This then has ramifications on biodiversity within the region as a whole.
Biodiversity and indeed human activity within polar regions are also ever increasingly becoming impacted by the loss of Arctic sea ice. Polar bears require a key balance of open water in which prey such as seals can come up for oxygen and rest, and therefore be vulnerable to attack, whilst also having enough ice so they can reach these areas where the seals will rest. However, with annual ice mass decreasing, polar bears have been forced to go to extreme lengths to find food. Just recently, it was reported 52 polar bears had invaded human settlements in their search for food in a remote group of Russian islands. Vermeer et al.'s 2013 paper highlighted how human settlements can also be hugely impacted by the decline of ice coverage, as its impacts on sea level rise and the ferocity of storms that make low-lying Arctic coastal regions susceptible to storm surges. As a result, the destruction of infrastructure and agriculture, many communities living in areas such as the Mackenzie Delta will be forced to migrate south from their homes and their communities. In conclusion, Arctic sea ice coverage is especially vulnerable to an increase in greenhouse gases in the atmosphere, and the ramifications of the decline of ice coverage have huge potential in terms of the damage it could cause to humans as well as the environment as a whole.